Hello, everyone. Today we are going to be learning about perfect squares and solving by undoing or using square roots. Perfect squares are going to set us up so that we can learn about our next topic for solving quadratics, which is completing the square. So to start off, our topic today is solving by undoing. Which we could also just say solving by using square roots. Solving by using square roots is something we can do when we have a term squared on one side of the equation. For example, x squared equals 4. If we're trying to solve for x, we can take the square root of both sides. And that's because the square root is a way to undo squared. So when we take the square root of x, when we take the square root of x squared, we end up with x. One thing to watch out for, though, thinking back to our unit on exponents, if we square root a number, we need to make sure that we take the positive and the negative square root of that, because positive 2 times positive 2 equals 4, but also negative 2 times negative 2 equals 4. So we have plus or minus 2 in this case. And this plus and minus is just a fast way to write down that x equals positive 2 or x equals negative 2. So these two mean the exact same thing. X is plus or minus 2. So we're solving by taking a square root. And we can do this when we have something called a perfect square on one side of the equation. A perfect square is just a number or polynomial, an expression that can be rewritten as another number slash polynomial squared. So we can rewrite this expression, this number polynomial, as another number or polynomial squared. So looking back at our first equation here, we have a perfect square on both sides of our equation, actually. If we think of numbers, number perfect squares are 1, 4, 9, 16. So we're kind of familiar with these. 1 is 1 squared, 4 can be rewritten as 2 squared, 9 is 3 squared, 16 is 4 squared, and so on. So on the left, these are all what we call perfect squares. We can also have polynomials that are perfect squares. For example, the x squared that we had on the left, that can be rewritten as x times x, or x squared. So we would consider this a perfect square, also x squared. We could have polynomials like x plus 2 squared is a perfect square. We could also write these out in standard form. So if we had x squared plus 6x plus 9, this is also a perfect square because when we factor this, we can rewrite this as x plus 3 times x plus 3, which is just x plus 3 squared. So here we have some examples of polynomial perfect squares. So sometimes we'll be given the polynomial squared. Sometimes we'll need to factor it to see if it's a perfect square. Perfect squares are helpful because when we have a perfect square, we can go ahead and solve by taking the square root of both sides for our first step. Let's go over another example. Let's say we start with x squared plus 6x plus 9 equals 25. And we're being asked to solve for x. So we could maybe subtract 25 and then try factoring. What I'm going to do instead is try and rewrite that left side as a perfect square. As we saw up here, we can rewrite x squared plus 6x plus 9 as x plus 3 squared. And then we can undo that square root sorry, we can undo that square by taking the square root of both sides. So square root of x plus 3 squared equals, and again, making sure we do plus or minus on the other side when we take the square root. So on the left here, the square root and the squared cancel out, so we just get x plus 3 equals plus or minus the square root of 25 is 5. So we got rid of that squared part by rewriting, factoring our quadratic, and then taking the square root of both sides. One note is we aren't quite done yet because we want to try and isolate x. We're trying to solve for x. So our final step would be to rewrite this. If we have anything on the same side as x, we want to rewrite this using the two forms up here. So using this form, instead of the plus or minus, we're going to split it up into two equations. X plus 3 equals positive 5, or x plus 3 equals negative 5. And then we'll solve for x in each of these equations. So subtract 3 from both sides, x equals 2. Or if we subtract 3 from both sides, we get x equals negative 8. So here we have our two solutions to our quadratic equation here that we started with. So whenever x isn't by itself, we want to make sure we split it up and then isolate x in both of the equations we end up with. So again, we started by factoring and then using the fact that we had a perfect square to take a square root, and then just isolating x from there. I also want to talk about what perfect squares look like geometrically. So if we think about them as shapes, for example, if we started with a number perfect square 4, which we know can be rewritten as 2 squared, we could also write this as a rectangle, or square, sorry, a square, with 4 parts. And on one side we have 2 parts. On the other side we have 2 parts. So the total number of squares we have in here is 4. So we have 4 of these. So perfect squares can be represented geometrically as a square. Another example, 9 is 3 squared. We can represent 9 with a square that has 9 smaller squares, 3 on this side, 3 on this side, and then the area, this area here is 9 squares total. So this is what number perfect squares look like if we rewrite them using boxes. We can also rewrite variable perfect squares using boxes. Let's take a look at x squared. For x squared, we can say this side is x, this side is x, and we have one x squared box here. So notice here, the number that we have inside of each of these is 1. We have 1 unit of area in each of these. Down here, our amount of area that we have is x squared area. So we're just calling this square, or this shape, x squared. If we had x plus 1 squared, well, we have x plus 1 on the top, and then x plus 1 on the bottom. So we end up with this x squared box here. We end up with 1x, so 1 times x here. We end up with 1x over here also. And then finally, this side, notice we have the 1 and the 1. So we just have 1 box left over, an area of 1 left over. So this is connected with our area model. So we're starting with the factors, and then we multiply using our area model. So we can rewrite perfect squares using this area model. I want to do one more example. Let's say we have x plus 3 squared. X plus 3 squared can be rewritten as x plus 3, x plus 3. And again, we start off with our x squared box here. Here we have 3 x's, so 1, 2, 3, x, x, x. Here we have 3 x's also. And so here I'm just writing out every single x as 1 unit. And then finally, we have 9 ones left over. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 ones left over, and these are all just ones when we multiply 3 by 3. So this is what our area model looks like when we rewrite polynomials that are perfect squares using the area model. And again, notice that this shape here is a rectangle, and furthermore, it's a square. So both of the sides are equal. Finally, if we rewrite this in standard form, we have 1x squared plus we have 3x's here and 3x's here. So our x's are kind of split in half, plus 3x plus 3x. And then finally, we have 9 ones down here, plus 9 ones. So at the end, we have an x squared plus 6x plus 9. So notice this number here is the number of ones that we ended up with. And this 6 is split in half in between these two areas here and here.